Okay, so hello everyone. Welcome to this second video uh, in Calculus 1. So today we'll start talking about functions. So basically a recap of whatever you have learned, but essentially. Um, okay, so what is a function? You all know. So you have a set of inputs, which we call a domain. And then you have outputs, which are contained inside a codomain. So this term perhaps is could be a new term for you. So codomain is a space that where you can find all the outputs. Okay, and set of these outputs is sometimes called the range. So come to that, but codomain is the space where outputs take their values. Okay. So you have a function, so domain, codomain, and there is this rule. So what is a function? If you recall, it's a rule. So there are three things to note in this definition. So first of all, what is the definition? It's a rule that assigns to each input a unique output. So first of all, it's a rule, and it has to assign each input. So you cannot leave out any of these inputs, and each input a unique output. So you cannot assign more than one output to each input. Okay, so we have to assign a unique output. So this is an example of a function. Each input has been assigned to a unique output, but this is not a function because this particular input is assigned to two different outputs. So the uniqueness part of this definition fails here. So this is not a function. However, there's a term for such a scenario, which is a relation. A relation. So f in this case is a relation. So a relation differs. It's a precursor of a function where this uniqueness does not hold. So we're not going to talk about relations here. So focus on functions. So some definitions of terms. So suppose you have a function from x, so from x to y. So x is called, once again, the domain, the codomain. So if f is the function, then y, which is equal to, so each x is assigned to some value in the codomain. So each input, for each input, we have a unique output, which is called the image of the input. So we'll call y the image of x if y equals to f of x, and we'll call x a pre-image of y. Okay. So notice the difference that we're using d for the image and a in case we have a pre-image. Why is that? Because this image is unique. Okay, so that's why we were saying the image of x, whereas the pre-image may not be unique. So that's why we are saying a pre-image of y. For example, if we look at this function, so if this is y, then it has two pre-images, right? So such a function sometimes is called a many-to-one function. Okay, you already know these things. Just to recap, so image is unique, pre-image is not necessarily unique. So range of f, another term, range is a subset of codomain which consists of all the images. So this range of f is consists of all the image points. So this of course is contained in the codomain, which in this case we're calling it to be y. Okay, so and then sometimes you're given a rule and you do not know whether it's a function. So how to check whether a given rule is a function or not? So it's pretty simple. So what you do is, suppose if x to y is so generally this expression is used to denote a function. So that's what we're using here. But by abuse of notation, I'm just saying that this is a rule and we do not know for sure whether it's a function or not. So how to check it's a function, if it's a function? So it's pretty simple. You look at two distinct image points. And so if f of x1 is not equal to f of x2, so two distinct image points, then this should imply x1 is not equal to x2. Okay, let's analyze this. So we are saying if, so for f to be a function, if you have two distinct image points, you cannot have the same image. That's what it's saying. So this sign is used for implications, right? If a statement A, usually, so let me quickly tell you, if you have a statement like, if a statement S1 holds, then a statement S2 also holds. Okay, so if we have a scenario like this, then we say that S1 implies S2. Okay, that's how implication works. So the truth of S1, the truth of if S1, then S2. So S1 implies S2. For example, if n is an integer, or if n is a natural number, then n is an integer. So that implication would be n belongs to n. So this symbol is reserved for natural numbers, implies n belongs to z, the set of, so this symbol is reserved for integers. So the statement that n is a natural number implies that n is an integer. So the reverse direction of this implication will not work here, because not every integer is a natural number. Only positive integers are natural numbers. Okay, so that's a slight digression to illustrate what this symbol means. Yeah, back to checking whether a given rule is a function. So we're saying that given two distinct image points, f of x1 not equal to f of x2, if f is a function, then x1 is not equal to x2. Why is that? If x1 becomes equals to x2, then you have a picture like this. So if x1 equals to x2 equals to a common value x, so then you have this picture going. So this is f of x, this is f of x, which would contradict the definition of a function, right? So you cannot have, once again, you cannot have one-to-many sort of a situation while defining a function. So this kind of thing cannot happen. So fx1 not equal to fx2 must imply that x1 is not equal to x2. Okay, so fx, hopefully it's clear. And the same statement can be restated by saying that if x1 is equal to x2, then fx1 must be equal to fx2. Why is that? So why is this statement same as this particular statement? It's pretty easy to see. See, if x1 equals to x2 and fx1 is not equal to fx2, then given that this statement holds, fx1 not equals to fx2 would imply x1 equals to x2, x1 not equals to x2. And this would contradict my initial assumption that x1 is equal to x2. So this statement over here clearly implies this statement. Similarly, this statement will also imply this statement over here. Why is that? Well, suppose this statement holds, that is, this is true, we have to prove this holds as well. So suppose fx1 is not equal to fx2. I have to show x1 is not equal to x2. What happens if fx1 is not equal to fx2 and x1 is equal to x2? See, if x1 is equal to x2, and I'm assuming that this statement is true, so x1 equals to x2 would imply fx1 equals to f of x2, which would contradict my initial assumption once again. So these two statements they're pretty much the same thing, okay? And so this highlighted statement over here gives us an easy way to check whether a given rule is a function or not. So for example, let's look at the function f the rule from R to R given by f of x equals to x squared. So is this a function? How we are going to check? Simply make use of this rule over here. So if all I have to do is simply check whether x1 equals to x2 implies x1 square equals to x2 square. Obviously, this is true because if two real numbers are equal, so will their squares be. So clearly, this rule is a function. Okay. All right. So that's how you check if a rule is a function. And then you have different kinds of function. Once again, you have studied this in your high school, one-one functions, onto functions. So one-one, I'm used to call them injective. So I'll use this term injective for one-one, surjective for onto. Okay. And if a function is both injective and surjective, we call it a bijective function. So typical example of an injective function is this particular picture where, so what is an injective function? Two different inputs cannot have the same output. So two different inputs will have two different outputs. Okay, so that's what an injective function is. And surjective means that everything in the codomain is an output. In other words, range is codomain. And what is range? Range is a set of all images, and this must be equal to the codomain for the function to be surjective by definition. So that's injective and surjective. So mathematical way of checking whether a function is injective or not. So two distinct inputs should imply their outputs are also distinct. So this can be mathematically stated as x1 not equal to x2 implies if x1 is not equal to fx2. And this is equivalent to saying that, like in the previous case, I'll let you think about this, that if x1 equals to fx2 should imply x1 equals to x2. So for a function to be injective, all you have to do is check this part over here. Okay, whether fx1 equals to fx2 implies x1 equals to x2. For example, I can use this to check whether this function fx equals to x squared is injective or not. So implication is other way around this time. So for injective, the other direction should hold. So this function, so I have to check whether x1 square equals to x2 square implies x1 equals to x2. Certainly not, because it's x1 square equals to x2 implies that either x1 equals to x2 or x1 equals to minus x2. So with certainty, we can't say that this x1 square equals to x2 square implies x1 equals to x2. So x1 equals to minus x2 is also a possibility. Therefore, by this criteria over here, we have that the function fx equals to x squared is not injective. So once again, we have two statements. This one is easier to use, and they're equivalent. And this verification is routine and straightforward. How to check whether some function is surjective or not? So here, suppose the function is f. So an output y would be equal to f of some input. So I have to check whether every y in the codomain is an output. So that means I have to check that at random y in the codomain, whether I can find an x or solve for an x, or find an x really, for which f of x is equal to y. We'll look at some examples in a second. Okay, and I mean, you already know this stuff. What is a bijective function? It's just a function which is both injective and surjective. Okay, so it looks a picture that comes to our mind immediately when we say bijective is the following. So I have okay, so let's look at some functions and see whether they're injective, surjective, or bijective, whatever. So fx equals to 2x plus 1. What do you think? So this is going to be clearly injective. So for injective so all I have to do is, so first of all, is this a function? I'll leave it up to you. Check. Okay. Is this injective? It's pretty easy to check that it's injective, because for injective, all you do is show that if 2x1 plus 1 is equal to 2x2 plus 1, then this should certainly imply that x1 equals to x2. And this is obviously easy to check, because this condition over here, after solving, you straight away get that x1 equals to x2. So this function is injective. How about surjective? For surjective, once again, like I said, I have to check whether every element in this codomain space is an image. So I take an y in the codomain space, and I have to check whether it's an image of some x in the domain. That means I have to check whether y is equal to 2x plus 1. And so it's pretty easy to, so pretty much you have to solve here, right? So for what x does this happen? So solve for x. So solving for x gives me x equals to y minus 1 by 2. So indeed there is some, so indeed there is some x for which 2x plus 1 equals to y, and that particular x is given by y minus 1 by 2. So this is also surjective, and therefore it's bijective. The same function f x equals to 2x plus 1, I've just changed the domain and the codomain slightly. So now the function is going from z to z. Okay. So how about injectivity, surjectivity, and bijectivity? So once again, this is something you should check on your own, pretty easy. So injectivity is not going to change, okay? Because yeah, it's, as you can see, surjectivity will change now, because if x is an integer, so injective is clear from the previous part. Surjectivity is not going to hold here, because if x is an integer, 2x plus 1 is an odd integer. So only odd integers are images here. So even integers don't have any pre-image. So even integers are not images. Therefore, this map is not surjective, and therefore it can't be bijective. So new function f going from r star. What is r star? R star is simply the punctured real line. That is, you remove 0 from real line. Okay. So all non-zero real numbers is denoted by r star. So f of r, f going from r star to r given by f of x equals to 1 by x. Is this injective, surjective, bijective? So once again, it's pretty easy to check that this function is injective. So once again, okay, I'll let you think about this, and it's not surjective. So injectivity is quite obvious. Surjectivity, okay. Is it surjective? No, it's not surjective because 0 is not an image. So clearly 0 is not an image because 1 over x equals to 0 would be an absurd situation, right? So no x will give you 0 as its pre-image. So surjectivity once again fails, and therefore it's not bijective. However, if you take a closer look, if I change this codomain to R star, then this function becomes surjective and hence bijective. Okay, so by manipulating the domain and the range, you can change the behavior of the function. Okay, and how about this last function, sine of x, going from R to the closed interval -1, 1. So it's clearly surjective, we all know. So surjectivity is there. And how about injectivity? Injectivity is clearly not there because, for example, sine of pi equals to sine of 0 equals to 0, right? So injectivity is missing here, and therefore the function is not injective, bijective. Okay, so those were some examples of various types of functions. So the good thing about bijective function is that you can invert the whole scene, in the sense that if f is a bijective function from x to y, by reversing these arrows, you can get a function from y to x, and that function is called the inverse function, f inverse. Okay, so the domain of f inverse is y, and the range is x. And on top of that, so f inverse is a function to be noted. And from this picture, we can also see that if f is, if bijective means that f inverse is also bijective here. So we are just reversing the arrows, right? We're doing nothing else. Of course, you have to, to make this f inverse meaningful, as a rule, you have to work, you might have to work a little bit harder, okay? But to see that this f inverse, a function, bijective function from y to x exists, you don't have to work hard. Okay, and so if x is equal to, so if x is assigned to y, that means y is the output of x, or y is equal to f of x, then this inverse function will send y back to x. Or in other words, we're going to have x equals to f inverse of y. So two important points to be noted here is that f inverse is a function, of course, and moreover, it's bijective. Okay. So generally, if you're given a bijective function, how to find its inverse? Okay. So once again, you have something that you have seen before in high school. So this function f R2R given by 2x plus 1, we saw that it's a bijective function. So how can we give its inverse? So we already have this equation y equals to 2x plus 1. So basically, to get the inverse, see that the role of x and y is interchanged. That means now I have to write x in terms of y. So basically, from this equation, I have to solve for x. So x is what function of y? That's what I have to find out. And that's not too hard to do here. So if y equals to 2x plus 1, x must be equal to y minus 1 by 2. And this is the inverse function we're looking for. So this is the f inverse y. Okay. So x equals to f inverse y. So my f inverse y, this f inverse function is basically y minus 1 by 2. And as is customary, we'll always change this argument of this function from y to x to denote it as a familiar function. So if f inverse x, the inverse function of 2x plus 1 is simply x minus 1 by 2. Okay, so there are other functions. For example, in your high school, you have studied about sine inverse of x, right? So we just said sine is not bijective. Then how come its inverse exists? So inverse of a function can be made to exist by restricting domain. Okay. For example, look at the function, or think about the function fx equals to x squared going from R to the set of non-negative real numbers, which I'm denoting by this symbol. So R with a bigger than equal to 0. So this function, once again, is not a bijective function because it fails to be injective. See, plus x and minus x both are sent to, both are being mapped to, or both are giving outputs x squared. Okay, so it fails to be injective, therefore it's not bijective. However, if I restrict my domain to non-negative real numbers, then this function becomes bijective. Okay, that's because, see, this function is clearly onto, and every non-negative real number has has two elements in it, two pre-images, right? So, for example, I mean, one is, so every x over here, every y over here has two pre-images, namely square root of y and minus square root of y. And by restricting our domain to only non-negative real numbers, we are getting rid of minus square root of y part. So there is only unique pre-image. And from there, we can see that we have the required injectivity. Okay, surjectivity is already there. So injectivity, by restricting the domain, we got the injectivity. So what is f inverse x in this case? So now it's bijective. So f inverse x is now the square root of x function. Needless to say. Okay, sine x and its inverse. So once again, sine x is not a bijective map when considered as a function from R to the closed interval -1, 1. We just saw that. But by restricting its domain to from minus pi by 2 to plus pi by 2, we can see that the function sine x becomes a bijective function. So now this function sine x is a bijective function, and the easiest, so why is it bijective? It's pretty, so it passes the horizontal line test, and so we'll talk about that in the next class. But from this graph also we can see that the function is bijective. So no two points in the domain have the same function values, or no two distinct inputs in the domain have the same output. You can see that, right? So typically, if a function is not injective, you'll have something like this. So this is the horizontal line test. So at two different points over the domain, the function will have the same value, right? So f of x1 is equal to f of x2. So that means the function fails the horizontal line test, and then the function is not injective. So this graph clearly passes the horizontal line test. So by restrict, now I can define my inverse function. Okay, so inverse function will now have its domain. So inverse of sine, which is called the arcsine or sine inverse, will have domain -1, 1, and its range will be minus pi by 2 to plus pi by 2. Okay, so next topic, once again, a familiar topic, composition of functions. So we have sets x, y, and z. We have function f going from x to y and g from y to z. So these two combine to give a function going from capital X to z. How is that? So each input here is, first of all, goes to y via f, and that y goes to z via g. And this in turn sends x to z via this factoring, right? So this, so x is being sent to y, which is f of x, and y is via g is sent to g of y. And so I can, so z, which is the image of y, is now g of y, which is equal to g of f of x, because y is f of x. So we write z as g of f of x. So g composed with f of x. Once again, so I'm not, I'm just recapitulating these things because I just found out that all these things are in the NCERT +2 syllabus, right? So most of you are, I mean, all of you are familiar with this. So, okay, so important things to note here is that domain of domain of this composition is going to be the domain of F. You can see that every x, every input in here, every x here can be sent to some element over here, because every x can be, so every x by definition of a function, every input over here has an output here, and every output here has an output here. So that means every input here in turn has an output in Z. So that means the range of G of, or the domain of G, this composition is going to be the domain of F. On the other hand, range is going to be a subset of the range of G. Why is that? That's because you may have possibilities like some element in capital Y, which is not in the range of F, but has an image over here. Okay, so some Y dash over here has an image Z dash, and suppose Z dash is, so this is like the unique image of Y dash. And suppose no other element of Y is being mapped to Z dash, right? So then Z dash will fail to be an image of an element from X, because it will only, Z dash can only be an image of an element from X, provided, you know, this its pre-image Y, which is just Y dash, has some pre-image in capital X. So let me know if you have any questions. So once again, so it's not necessary that, you know, every element of the range of G will be in the range of G of F because of this scenario. Okay, so a thing that is not obvious from this picture is that, you know, so when does this composition really make sense? It makes sense when range of F is contained in the domain of G. So here in this picture, this assumption was already made, that I'm assuming that every input in X has an output in Y. And unless and until it has an output in Y, that means until and unless that range of F is contained in Y, I won't be able to send it to Z, right? So for a composition to make sense, range of the first function should be contained in the domain of the second function. Okay, some interesting compositions is if F is bijective, what happens if I compose F with its inverse? So basically the composition gives you identity on X. So first of all, inverse means, so if X goes to Y, then F inverse is going to send Y back to X. So if I put X here, just to understand this composition a little better, so X is being sent to Y via F, and then Y via F inverse is being sent to this X again. So this composition of F inverse is basically taking X to X. So it's the identity map on X. Similarly, composing F with F inverse, it gives you the identity map on Y. So it's also interesting to study behavior of different types of functions under composition. Okay. So first of all, composition of two same kind of functions gives you a similar kind of function. For example, composition of two bijectives give you a bijective. Composition of two injectives give you an injective, and composition of two surjectives give you a surjective. So so bijective will be clear moment we understand composition of two injectives give you injective, and composition of two surjectives give you surjective. Because bijective is both injective and surjective, so composition of two bijectives naturally will be a bijective, provided we can show that composition of two injectives is going to be an injective. So composition of two injectives has to be an injective. Why? Why is that? That's because, see, two inputs here, two distinct inputs here will have two distinct outputs in the intermediate set Y, and since this, because the first map is injective, and these two outputs, on the other hand, they're going to have two distinct outputs here in Z, because this map is also an injective map. Therefore, the composition is giving you, and so this initial two inputs will have two distinct outputs in Z, in this final set. So composition of two injectives always is going to give you an injective function. How about composition of two surjectives? Composition of two surjectives is always going to give you a surjective. Why is that? That's because you take any element in the final set Z. So this is X, this is Y, this is Z as per our notations. So you take any element here. So since G is surjective, so it will have a preimage here. And since F is surjective, this particular preimage of this point will have a preimage here. So surjectivity of G guarantees a preimage here, and surjectivity of F guarantees a preimage here. So that means this thing under the composition will have a preimage. So composition of two surjectives is surjective. And therefore it follows that composition of two bijective maps is a bijective map. What happens if I mix things up a little bit? What happens if I compose an injective with a surjective? So the result cannot be predicted in general. That's the point. So in this particular scenario, we can see that composition of an injective with a surjective giving me an injective as well as a surjective map or a bijective map. So it's pretty clear. I'll let you think about why this is working here. Okay. But on the other hand, in this particular scenario, composition of injective and a surjective fails to be bijective because it's not injective anymore. See, for example, this composition is not injective because these two inputs have a common output in the final set. So this composition cannot be injective. Therefore, it can't be bijective. Okay. But nevertheless, the first map is injective, the second map is surjective. Okay, so let's make things a little bit more interesting by asking the reverse question. So suppose I tell you what the composition of two functions is, and then ask you to say something about the individual functions themselves. For example, if I tell you that composition of two functions is injective, can you say something about this function's GMF? Well, if the composition is injective, it's the immediate consequence of that is, or immediately we can say from there, is that this first function f must be injective. Why is that? If the first function f is not injective, then we have something like this going, and then so these 2 points have so f is not injective, so these 2 points have a common output. These 2 inputs have a common output, and this has an output here. So in the end, these 2 distinct inputs will have a common output in the final set Z, right? And that would mean that the composition is not injective. So the first function must be injective. Similarly, if the composition is surjective, what can I, what if, I mean, what can we say about these individual functions? Well, all we can say is that G must be surjective. Why is that? That's because if G is not surjective, then GOF cannot be surjective. Why is that? That's because this particular, so G is not surjective, there is something that is left out. There's some point in the codomain that is not an output of G under G, right? So if this means this does not have a preimage here, so how can it even have a preimage here? So these elements cannot be linked to this. Okay, so G has to be surjective for this composition to be surjective. So from this two, we deduce that if GOF, the composition is bijective, then from the first part, we can find out that if this F must be injected, and from the second part, we have that G is surjective. So the composition is bijective, the first function is injective, second function is whichever you call first or second, I don't know. So if F is injective, G is surjective. Okay, so that brings us to the last topic of this class, that is the cardinality of sets. So why are we studying this? This is because this is one of the applications of bijective functions. So using bijective functions, you can study the cardinality of sets. So let's find out how. So what is the cardinality of a set? Roughly speaking, so this is not the correct definition. Roughly speaking, it's the number of elements of A. So if A is finite, then this is exactly this. You can remove that roughly if A is finite. So it's exactly equal to the number of elements in if A is finite. So things get a little funky when A becomes infinite. So let's look at some examples. What is the cardinality of the empty set? Is there are no elements here, so cardinality is 0. Like I said, finite set is pretty easy. So suppose you have 1, 2, 3, 4 up till n positive integers. So cardinality is just n. How about the set of natural numbers? There are infinitely many. Cardinality is infinity. How about the set of reals? It's also infinity. The question is, are these two infinities the same kind of infinities? So, or in other words, we're asking whether we can say from here that cardinality of n is same as the cardinality of R. And so answer turns out to be a little bit twisted, and the answer is first of all no. And why is that? That's because n turns out to be countably infinite. So there's a concept which I'll momentarily introduce, but so this I'm not going to discuss this in this primary lectures. Okay, so I'll share a supplementary lecture on this countability stuff. Okay, so that is not a part of the course syllabus, so that's optional. So I'm going to share a lecture on that. So if you have a taste for abstract mathematics, please have a look at it. Otherwise, just forget about it. But yeah, so these are two different kinds of infinities. That's the point. This kind of infinity is called countably infinite. To make sense of this, we just quickly review this bijection maps. So suppose you have a bijection from X to Y, then we use the symbol X is similar to Y. Okay. So bijection kind of gives you, or a bijection from X to Y kind of tells you that X and Y have the same cardinality. So that is the correct notion of cardinality. So if you can find a bijection from X to Y, then you can say that X and Y have the same cardinality. It turns out that you cannot find a bijection from the set of natural numbers to the real numbers. Therefore, they have different cardinalities. So I'll talk about that in a second, but the similarity satisfies these three properties. I don't know if you have heard about equivalence relation, you will recognize this immediately. So first of all, X is always similar to itself because the identity map is a bijection from X to X. X is similar to Y, then Y is similar to X. Why is that? Because if there is a bijection from X to Y, I can always find the inverse map, which is also bijection, and from Y to X. X is similar to Y and Y is similar to Z, then X is similar to Z. This follows from composition of two bijective maps, giving you a bijective map. So X to Y, there's a bijection, Y to Z, there's a bijection. Compose those to get a map from X to Z, and we saw that composition of two bijections, the bijections. So yeah, this thing. Okay, so two sets A and B. So this is the correct definition of cardinality. So two sets A and B are said to have the same cardinality provided they're similar. That is, if you can find a bijection from A to B. So with this definition, we define a countably infinite set. Okay. So what is a countably infinite set? It is a set, it is an infinite set which is similar to n. That means you can find a bijection from n to a. So such sets are called countably infinite. Okay, so some immediate examples. The set of the reciprocals of natural numbers. This is an example of a countable set. And this is intuitively clear why this is countably infinite, because there is an obvious map from n to a given by f of n equals to 1 by n. And it's easy to check that this is a bijective map. So slightly more non-trivial example, which is not obvious, is that Z is similar to N. That means you can find a bijection from N to Z. And this is slightly counterintuitive because Z has more number of elements than N per se, because there are both positive and negative integers. But as far as the cardinality is concerned, we'll say that Z and N, they have the same number of elements because I can find a bijection from N to Z. And that too as follows. So the plan is to send all the even integers or map all the even integers or even positive numbers to, I'm sorry. Plan is to map all the even natural numbers to positive integers and odd natural numbers to negative integers in the following fashion. So fn is n by 2 if n is even, and fn is minus n minus 1 by 2 if n is odd. So if we put some first few values of n, you will find out exactly the picture that is we are trying to present here, that by this map, 2, this map is going to 1, 4 is going to 2, 6 is going to 3, so on. On the other hand, the odd integers, 1 is going to 0, okay, 3 is going to minus 1, 5 is going to minus 2, and so on. See, all the even natural numbers are mapped to positive integers, 1, 2, 3, 4, so on. And odd natural numbers are mapped to 0, minus 1, all the non-positive integers, minus 1, minus 2, so on. And clearly you can see that this map is also a bijection. From this distribution is pretty clear. And you can, if you want, you can make things more rigorous, okay? Okay, so I'll end this with a couple of more comments. So what's highly counterintuitive is that Q has the same cardinality as the set of natural numbers, because Q, there, so Q, if you know something about Q, uh, they are densely distributed on the real number line. Between any two numbers, you can find a rational. So you would expect to have a lot more rationals than the natural numbers, but it turns out they have the same number of elements pretty much by the definition. Okay, so this means there is a bijection from N to Q. So once again, this will not be proved here, but in that supplementary lecture, we'll find a proof of this fact. R is not, in fact, yeah, R is not similar to N. We will also prove this. So this also requires some proving, okay, that R is not similar, you cannot find a bijection from N to R. Okay. You can further show that this, whenever a subset of real numbers is countably infinite, it occupies really no space on the real line. That means total length of the numbers of a countably infinite set or subset of R is 0. So in one of the upcoming lectures, I'll try to make this idea a little bit more precise, but that's what it is. So for example, here, what this, so let's think about what this really means. So this means that, the total length of rational numbers on the real number line is really 0. So they contribute almost nothing to the whole real line. So that means they're more irrational numbers in some sense than the rational numbers. Or to make it even more precise, suppose I color, this rational numbers by white, and I label the irrational numbers by black, and then I look at the real number line after labeling the rationals and irrationals by white and black respectively. I look at the real number line from certain distance. All I will find is just a black line. So I won't be able to distinguish those little white spots, white holes in the real number line from a distance. That's because there are more rationals occupy almost no space on the real line. Okay, so I'll leave it right there. And next lecture we'll talk about real valued functions, a little bit more on that, and different subsets of real number.